I'd like to thank the organizers for this opportunity to speak. The title, Geometric Approach to Constructing Conformal Nets. The idea that I had, that I want to talk about, is relationship between different formulations of two-dimensional chiral conformal field theory, one of which a vertex operator algebra, which at least as I scanned the titles of talks for the conference seems like is going to be a bit of a theme going forward. The geometric, for the conformal field theory, I'm really thinking about VOAs. So it's talking about how to think about conformal nets, which I'll define briefly, which I'm interested in coming from the world of subfactors in terms of vertex operator algebras. So I'm going to start by talking a little bit about what VOAs are, giving a non-traditional definition, which hopefully will at least justify the word geometric in the title. So what's not a VOA? Well, what I would call, if you add enough adjectives, unitary, nice VOA, is the following information. Well, it's a Hilbert space. We'll call H0, and the following data. Well, for every genus 0 Riemann surface, I'll draw on the plane a linear map. Call the surface sigma. T sigma from a tensor product of the incoming boundary to one copy on the outside. So what do I mean? I'm thinking of there being a bunch of incoming boundary components and one outgoing boundary component. This is what you'd call maybe a genus 0 Siegel CFT, but I'm going to call a VOA. This is just like a functorial field theory, but in terms of many to one Riemann surfaces. And these maps have to satisfy some properties, namely they should be invariant under holomorphic isomorphism, so it doesn't depend on any embedding of this domain into the plane, simply on the as a complex manifold, and they need to be compatible with gluing. So that is, if I think about gluing the outgoing exterior circle of one of these surfaces into another, that should correspond to composition of maps. As they're complex manifolds, you have to be a little bit careful about how you glue them. So I'm going to insist that the boundaries come parametrized, that each boundary component would have a diffeomorphism to the circle, and when it comes time to glue them, it would just glue along the diffeomorphism. Don't want to say much about it, but I'm thinking of the boundaries circles being parameterized. Okay. This is not the definition you might expect the VOA. And then I guess I should say one more. This is supposed to be holomorphic. Be a little bit vague, but you could think about, for instance, as I move the center, I could think about translating one of those little pieces cut out. That could be a function of a complex variable. I have a map for each one, and I want that to vary holomorphically.
What if you reparameterize the boundaries?
Yeah, so there's the that gives you some action of the diffeomorphism group of the circle. You insist that this action have positive energy, which is the equivalent. If you analytically continue the rotation inside the circle, you want this to be contracted. So this is what I'm calling a VOA. And I should show you, at least for those who like VOAs, how to recover the familiar features you can be looking for. what does this provide you? Well, the disk, there's the unit disk with boundary parameterized by the identity. This should be a map from 0 incoming boundary components, that is from the complex numbers, to the Hilbert space. So this picks out a vector. This is the vacuum vector. What else does it give you? Well, you can put correlation functions in this context. If I want to compute correlation functions, say I have some vectors in the Hilbert space. I have treated as an operator algebra, so I have to use lowercase Greek letters. Some states inserted at some points z1, z2, z3. Well, I get a number by cutting out a disk from each one. And then I have a map. If I take this surface sigma, then the correlation functions are just given by the vacuum expectations of this map. So this has, in Siegel's original formulation of this geometric version of conformal field theory, this is the kind of thing he had in mind. But we're no longer just thinking about inserting states at points, we're also allowing ourselves to insert points in a disk, a more analytic framework. So we have the vacuum vector, we have the correlation functions, the vacuum expectation values. And exactly the fact that this should be holomorphic in the insertion points is one of the requirements that I insisted at the beginning. So you have holomorphic correlation functions embedded. So these are the kinds of things you expect to see from a VOA, and they do show up in this definition.
So in the algebraic definition, you also have the state field correspondence. Why? How do you get?
Thank you. So in particular, the thing you'd be expecting to see is a state field correspondence. Well, if I take a two-punctured disk with two circles removed, it's biholomorphic to one of this form. I can center one of the disks. I can, in particular, make the boundaries circles. I can center one of the disks at 0. The other disk becomes centered at some other point, z, and they have some radii, which I'll call S and R. Can map the exterior circle to the unit disk. So this is any three-punctured sphere, a sphere with 3 holes removed, and this corresponds to the state field correspondence. So if this is sigma, then the corresponding map is just almost the vertex operators, but you have to regularize with these terms, s to the L0, r to the L0. If you don't, if you're not familiar with VOAs, then don't worry about it. The general idea is that if the operators from a VOA are not continuous, and these are mollification terms that pick up the geometry. So you start out with this operator which isn't continuous, and you use the geometry as these internal radii. And I think I switched RNS.
Do these factors also appear in your correlation function?
Well, so you have to be a little bit careful as you define the state side would correspond to the state sitting inside a disk of radius 1. And then if you want to change the size of that disk to insert it, then you pick up a scaling dimension, which will exactly cancel that out. A little sloppy about that. You can translate directly. If you have VOA, you can write down the thing you want to assign to a surface such as this, and that tells you that if there is a corresponding geometric VOA, whatever you want to call this structure I've defined, it's at least unique. There's an existence question, but you know what it's supposed to look like. And it has all the features you expect. You recover the state field correspondence, the correlation functions, and all of that. Great. In this formulation, you can also see For instance, one of the things you might be interested in the VOA are the genus 1 correlation functions assigned to the torus, where you see vector valued modular forms. And that just corresponds to taking the trace of a map like this. That is gluing the interior circle to the exterior circle. And you can see the torus showing it right before your eyes. So I've said the term Siegel's CFT a few times now. So Siegel's definition of a CFT was not just this little genus 0 piece, but in fact a generalization of this definition where you have, you think of any Riemann surface compatible with gluing. And I don't want to get into that too much. So I want to get to subfactors. The goal is to show the broad claim that I'd like to make is that if you think of a VOA now as this holomorphic operator valued function on the moduli space of ways of these genus 0 Riemann surfaces, that a conformal net and subfactors corresponds to certain boundary values. That is, some certain ways of going off to infinity in this moduli space. So I'm going to try to make that a little more precise. So to get subfactors, we're going to need notion of a module over VOA. And again, there's an algebraic definition that you might be familiar with, which I'm not going to give. Instead, I'm going to just slightly modify this definition. So a module over such a thing, well, is a Hilbert space H lambda and a family of continuous linear maps between Hilbert space assigned to not just any surface, but I'm going to label the boundary components of the surface. One of the incoming ones gets labeled by lambda, the outgoing one gets labeled by lambda, and the other incoming ones get labeled by lambda. And now you should have a map over the tensor product, one copy of H lambda between the Hilbert spaces corresponding to the particular label. And again, you need compatibility with gluing. You could think about two different ways of cutting up this surface. I could cut out the two pieces labeled by 0, and that's a map from the VOA, and this composition of two ways. Or I could think of cutting it a different way, and now you have two module actions. So this is just a generalization of the notion of module over a commutative algebra. In fact, if you assume that this only has topological dependence instead of conformal dependence, this is exactly the notion of module over a commutative algebra.
Is lambda just one other symbol, or is it a whole?
One other symbol. You can imagine having many. So I would be interested in a finite set, but at the moment I'm just using lambda as the name of the representation. Yeah, it's not a spectral parameter, or at least not at the moment. And like a commutative algebra, we have a notion of tensor product of modules, which you can express geometrically as well. In the algebra, if you're familiar with the algebraic setting, you'd be looking for words like intertwining operator, maybe. To have a tensor product, I would be looking for maps, a way of assigning, say I have two modules, lambda and mu. I want a way of assigning a map to surfaces like this. So this would be a map from H lambda, tensor H mu, tensor many copies of the algebra itself to some other module in a way that's compatible with gluing. So the space of vector space of all such maps, all ways of assigning bounded maps to surfaces with two input labels corresponds to the Hom space for the tensor product. So this is just what you're used to seeing. So this should be ideally in nice examples of finite dimensional vector space map satisfying that problem. Okay. You okay? Any questions?
What was this last remark? This is something finite-dimensional vector space.
So ideally, so what you're looking for is called an intertwining operator. If you're familiar with the VOA language, it would be a way for any Riemann surface labeled as such to provide a linear map, and then you could look at the vector space of all such ways of making that assignment. That would be some vector space, but ideally this should be finite dimensional. This should be the intertwiner space when the mu. All right. I want to just conclude my introduction to VOAs as I want to talk about them with sort of the highlights in terms of examples of things which count as nice according to the definition. That is, a nice VOA is one with this geometric structure. The examples, well, you have compact simply connected Lie groups G at positive integral level K. Favorite VOAs. We also have the Virasoro minimal models, which we've heard about earlier, the Virasoro discrete series.
Can I come back to the tensor product? I think I didn't understand. So you're plugging in two modules, right? So the lambda thing has all this multiplication in it, and the new thing as well. So how is it coming up in this?
So the idea is that you should be able to assign these maps in such a way that are compatible with gluing. So I have, for instance, I could think about cutting this way.
Okay, and then you're using the given. Okay, thank you.
Or you could imagine you have two zeros and they all interact.
But I mean, so a module there was an h lambda. If you do this, I mean, there's no h lambda yet.
So there's so I have three modules. So I want to think about the Hom space. If I want to define a tensor product, I want to think about the Hom space.
Yeah, but I mean, how do you know that the domain exists? That there is a module which has these forms?
Well, the zero map does it. So you have two modules, h lambda mu and nu, and I will want to look for linear maps that satisfy certain commutation relations. And the zero map will certainly do it. Maybe there are no others. And their existence tells you about the fusion rule in this in the category of representations for the VOA. So for example, if you're familiar with the theory of VOAs, and you have an intertwining operator of type lambda mu nu, this surface gets assigned the intertwining operator. And whether there exists any is something that you need to calculate.
But I mean, what is the Hilbert space of this new tensor product?
It's not defined.
I'm not giving you, I'm not telling you the tensor product. If you like, these are finite dimensional vector spaces. There aren't that many choices, but the actual putting a canonical inner product on it is a great question, which is open to my knowledge.
He's defining the function that might or might not be represented by the object, h lambda tensor h mu.
The unitary structure of this tensor categories, I think, is something that's pretty open at the moment. So these are the examples mostly be interested in that fit into this framework for which there exists this broader geometric structure. And the question is, what does any of this have to do with subfactors?
James, I think it makes sense to comment that these examples have been constructed in a setup where these Hilbert spaces are not really Hilbert spaces, and that they have not been.
No, these are all inside the free fermion. Sorry, yeah. These are all, many of these. And then, that's right. So in terms of the general theory, there are only many, but not all of these have been constructed in this framework, in all of these. So not every level for a group. That's right. One of the nice things about looking at different axiomatizations of a single physical object in different mathematical fields is that you're able to compare across the different axiomatizations. You have a model way as it shows up in one axiomatization, as it shows up in the other, and you can try to relate them by the fact that they're supposed to encode the same physical ideas. So where the subfactors show up is in algebraic conformal field theory, which I'll quickly introduce. This is in the framework of nets of local algebras. So in chiral conformal field theory, that was good. The setup is as follows. Space, what one studies is families of von Neumann algebras, given the unit circle S1 and an interval I on the circle. We have an assignment A of I of von Neumann algebra, which again have to satisfy various properties, which I don't want to say too much about, but the most important property being these must commute. When the intervals are far away, which in this case just means they don't intersect. You have families of commuting von Neumann algebras. In practice, these algebras will all be the same. They'll all be the hyperfinite 3-1 factor, but the inclusions. So another axiom is that if you have a subinterval, it must be a subalgebra. You have these families of inclusions encode information.
An algebra for the circle as well, something where everything lives in.
Yeah. So these are all supposed to be on the same von Neumann algebra on a common Hilbert space. The algebra assigned to the circle would probably be, in this case, just view. And again, there's a notion of representation, which is more or less writes itself. You have a family of von Neumann algebras, and a representation is a family of representations. I'll call my representation again lambda. I have a Hilbert space H lambda, and for every interval I, I have a star homomorphism acting on some other Hilbert space, compatible with inclusion. And from this, we have subfactors. Each of these local algebras is a factor. So I look at the image of one local algebra. It's supposed to commute with the algebra assigned to the complementary interval. So that gives me an inclusion. Sorry, pi is supposed to be lambda. So you think of cutting the circle into two pieces, an interval and its complement. You look at how they're represented on some Hilbert space, they commute, and the inclusion of one into the other will be a subfactor, often called Jones-Wassermann subfactors in this context. So part of it, in many ways, the inspiration for what I'm trying to do comes from a paper of Antony Wassermann, where he analyzes these subfactors, the original goal being to construct the subfactors of type A of index less than 4. So these were the ones Vaughan constructed as the original subfactors of index less than 4 in his 1983 paper, which we've heard about. But it's roughly a combinatorial construction. And what Wassermann gave a proof, which is corresponding to SU2 at positive level, you can actually construct these subfactors not just combinatorially, but coming from conformal field theory. So these subfactors and their analysis is the original motivation. For me, anyway. Not very good at that. I want to organize things with the following definition. an algebraic CFT, conformal net is called rational if it has finitely many classes of representation, each with finite index, such that the subfactor associated has finite index. So finitely representations, all with finite index. So this definition is the result of considerable evolution. Actually, the original term is defined by Kwagashi, Longo, and Yuger as something they called completely rational, which had additional assumptions, additional requirements, and then with a significant work over many years, it's been whittled down to, at this point, is just this definition. Maybe as you want. And the goal is the question is how many examples of these are there?
Irreducible representation?
Finally, yeah.
Irreducible or decomposable?
Semi-simple.
So you know what? Yeah, of course it's semi-simple.
Sorry, I shouldn't say, yeah. I don't know about semi-simple. There are complements, yeah. Okay. So what are the examples that satisfy the rationality property? Well, of the ones up there, Antony Wassermann's work was SUN at level K. He constructed a bunch of representations and showed they all had finite index. Feng Shu later showed that these were actually all the representations, proving that those were rational. There's a bit of an interesting story with the Virasoro discrete series, proving that they had this property. There was a PhD thesis that did a lot of work to that direction by Terence Loke, right here in Cambridge, for which there are maybe a few issues, and then another proof was given by Kwagashi and Longo using other techniques. So SUN at level K, a few other examples in the Virasoro discrete series are known to be rational, but in particular, E8 at level 7000, it's an open question, or E8 at level 2. Okay. E8 at level 1 is, there's no representations. And this is still open. This thing rationality which can be established for VOAs is seems to be much harder to establish in the case of conformal nets. So that's all by way of motivation. And the goal is to present a relationship between VOAs and conformal nets. The way I think about it is the VOA provides holomorphic operator valued function. Well, that's on some complex domain. The conformal net is living on the boundary. As if you try to look at the operators assigned by the VOA, go off to infinity in some direction, and you'll land on an operator in a conformal net. What is the path from VOAs to conformal nets? I should say there's, in the lore of the subject going back, there's a construction which isn't the one I'm going to talk about. Option number 1, by smeared fields. That is, you take this holomorphic operator valued function and think of it as a function on the circle, integrate against a compactly supported smooth function. In some interval, and there should be some operator, and you look at all of the von Neumann algebra generated by these operators. There's a significant technical difficulty here, the fact that these are unbounded. And so a lot of work was done in the direction of making this precise and rigorous by Sebastiano Carpi, Yosuke Kwagashi, Roberto Longo, Nishi Weiner, proving that you get conformal nets in basically every known example. This is not what I want to talk about. So I'm talking about option 2. a picture that André Henriques drew for me a couple of years ago. What André says, you can tell me if I'm incorrect. Do you want to know how I picture an element of a conformal net? And he drew a picture, something like this. I can't. Some little bit of surface, like the operators you might expect from a VOA, from a genus 0 Siegel CFT, but now it's just some interval along the boundary, and maybe some states inserted in the middle. And these are things now, if this is some interval, you can multiply them, and out is supposed to come the conformal net. So the construction, have in mind, is to try to complete this circle. And now what you have, think of this as a boundary value of the operators assigned by a VOA in the following way. So let's say I take VOA allows me to assign maps to surfaces of the following form. I want you should think about this part as being thin, and maybe I can put some extra disks here if I like. You get a map from here, 4 copies of the algebra to 1, and try to take the limit as this becomes thin. So as this surface gets squeezed, at each step along the way, we have an operator assigned by the VOA, but you're doing something really unpleasant to this complex surface, trying to squeeze it thin, and you can ask, does this converge to some operator, which we would then say is assigned say to this. So when I draw this picture, what I'm thinking of is a Riemann surface, but not quite. It's a Riemann surface where you're allowing it to have thickness 0 along part of the boundary, which if you like can be understood as a limit as you just squeeze this tighter along the way. And at each step I have an operator here. You can ask, does this converge? And more generally, does this converge to a continuous map on the Hilbert space?
From that we need an algebra for intervals. What is the interval here? Is it the thin part?
It's in this case, it's the thick part. I'll be more precise about that in a second. The idea is that now, so if you remember, you can tell the different intervals apart because the boundary is supposed to be parametrized. So we can ask that. So just to be more precise, this is the definition that we're hoping. Is this limit operator bounded? And if so,
0 that it exists in the first place? Or
is it
clear that it-
well, for an operator from a Hilbert space to a Hilbert space, if it's defined everywhere, then it's going to be continuous. You can't help it. But in this case, it converges on a dense domain. It's easy to see, and then is it bounded? Does it converge everywhere?
Dense domain which is converged is clear.
Yeah, that's not hard to show. In particular, if you apply the vacuum vector, then there's nothing going wrong because it just gets filled in, and then you can sort of inductively. Yeah, on the dense domain is fine. So you try to define the local algebra to be, if I call operator like this, T sigma.
Do you have a precise recipe how you make the surface and how you make it small, or is it independent of? I mean,
in this case, the recipe I have in mind is, actually it doesn't work with the way I drew the picture, like that. It's just add an annulus, but it. Let me state. I'll state a theorem in a second. In a sense, the thing that in the examples where I do everything I assign is to this object, and then you can prove that it's this limit. There's actually a thing assigned to this object. So So what do the local operators in this algebra look like? Well, you take some degenerate Riemann surface like this with a hole. You take some vector, which you're going to insert as one of the inputs. This is a map with 2 inputs. So you look at all the ways that fix one of the inputs, and that gives you a map from the space to itself, one input, one output, over all choices in all geometries, where this is labeled by the interval I. And you look at the von Neumann algebra they generate. So you'd like this to be a conformal net. So this realizes the algebras of the operators of the local algebras as limits of operators assigned to the VOA as you go off in the moduli space of configurations of these sorts of Riemann surfaces towards this point in infinity. And so the theorem is that this in fact works for a large number of examples. They have to be slightly, I can only prove that the limit is bounded in some nice cases, but it's enough to get a conformal net. So let me state a theorem. So V is a unitary sub-VOA of n free fermions. Then enough of these operators are bounded that you generate a conformal net. So in addition to checking the boundedness of these operators that are supposed to generate your local algebras, you also need to check that they commute in different intervals and so on. So this does indeed produce a conformal net. So if you draw a picture, such as this one, and decide what states you want to stick in here, you have a bounded local operator. So these are, I mentioned earlier that there's another approach. So these conformal nets constructed by Karpy, Kodashi, Longo, and Viner, and this gives the same result. The main difference being, as I see an advantage here, is that you can actually look and see things that are limits of vertex operators in the local algebra that's generated by bounded.
Are the conditions also the same between option 1 and your option? That it's a unitary sub-VOA of the
no, their construction is significantly broader. Significantly is moderately, fairly, significantly is broader. So the question that this demands is, what examples arise this way? Well, I don't have them on the board anymore, of the WCW models. You get every group, but not at every level. So there is some number, which I'll call delta G times K. So there's some lowest common denominator. So for instance, for SUN, this number is 1, and you get all levels. For G2, this number is 2, and you get even levels. For E8, the number is 30 or 60, and you get all levels multiple of 60. So you get every group at infinitely many levels, but maybe not every level. So the number is just the Dinkin index of the smallest representation of the group. And you get the minimal models. This construction, so the free fermion is a super VOA. So you can also do it with Z2 graded theories. You get the n equals 1 super Virasoro and many more. This gives you a construction of those conformal nets. 15 minutes, is that right?
No, 15. You started late.
This is good, but we don't have subfactors yet. Well, so as you know, just from the commutative case, if you have an algebra and a subalgebra, you can decompose the big algebra into modules for the smaller algebra. So the theorem, the theorem I just mentioned is on the archive at the moment. The next one I was hoping to have by today, but it didn't really come together. Suppose I have a module. Suppose V is also rational in the VOA setting, which is generally easier to establish. For instance, all of the WZW models, G at level K, has been established. Suppose V is also rational. You take some submodule of n free fermions for V. then you can construct a representation for the net coming from this VOA, and in fact, you can prove that it has finite index. This is, in fact, you can do better. You can say things about the fusion rules that in the tensor category of representations of the conformal net, sort of analogous to what Antony Wassermann did for SUN. So this is in many ways inspired by what Antony did. It's a modification of his approach using this sort of geometric idea, and it gives you sort of recovers as a corollary Antony's results on SUN. It recovers the fusion rules for the minimal models, and for many other examples, if in a broader context of just submodules of free fermion, you can get finite index subfactors. Exciting for me. You can even do a little bit better, and in a lot of the cases prove that there are only finitely many representations as well. So you can prove, using conformal inclusions, complete rationality of a bunch of models at the moment. So there's still quite a bit of work I need to do to go in and see exactly which examples show up. At the moment, all I can see is that it seems to recover all the known results, at least, in one place. So I want to say at least a little bit about the proof. Boundedness. So you have a limit of operators. Maybe I have this thing, parameter r, I have 1. I want to think about what happens to this limit as r goes down to 1. You have a bunch of operators. How do you control the norm? How do you show that the limit is bounded? This turns out to be a question in complex function theory, which I was very excited when I first realized this. I figured I could talk to experts in complex function theory, but it seemed there's what seems to me a fairly basic question, but one that maybe needs more study. It's the following situation. So given the unit disk, you need to define the Hardy space of the disk as holomorphic functions on the disk with L2 boundary values. Like holomorphic functions on the disk, non-tangential L2 boundary values. And I now take my favorite smooth closed curve inside the disk, called gamma, and look at the restriction operator. Given a holomorphic function with L2 boundary values, I'd simply restrict to an L2 function on gamma. It's fairly natural. And you're going to ask, what are the properties? Well, it's always going to be bounded. Takes maybe a little bit to see, but this is going to be a bounded operator. But the norm can be as large as you like. Particularly, it's at least as large as the length of this curve. So as the curve gets very long and wiggly, this operator has large norm. But it turns out what you need to know so that limit in the VOA setting gives a bounded operator for the free fermion. Following question. Norm is going to be at least 1, and you want to try to approximate it by finite rank operators. And the question is, how well can you approximate it by finite rank operators? Define the singular values to be the minimum, the n singular value is the minimal norm of a rank n perturbation of the operator. This will be a decreasing sequence. It starts at the norm, converges to some limit, which may or may not be 0. That limit is called the essential norm. It's the norm in the mod compact operators in the Kalkin algebra. And the condition, so the limit operator in the sense, as I described for the free fermion, is bounded if and only if the product of this sequence converges. So the first term can be as large as you like. You can make the norm large. So this is maybe at first glance a scary condition. And so I don't have the general answer to this. As I said, it only works in some cases, which happen to be enough to generate a conformal net.
Which gamma? I mean, it depends on gamma, right?
It depends on gamma, absolutely.
So this condition.
So this is gamma, this curve here.
Okay.
So if the curve doesn't touch the boundary, the sequence converges to 0, and this product is 0, and everything is fine. So it becomes interesting when it touches the boundary but doesn't coincide with it. And we proved so part of the proof of the result I mentioned was that in at least enough cases this is finite, but you could ask in general, and that's general theorem I have, which is a recent result with Mihai Putinar, an approximation theory. Found it between 1 and O of 1 over n. 1 plus O of 1 over n. So this is a very tantalizing general result. We'd like this product to converge. You know it does in some cases, in a lot of cases, but without general. But this alone seems to be an interesting question in approximation theory. I remain interested in trying to get this to a 1 over n to the 1 plus epsilon.
In the construction of the conformal net, you had a second pole in this area where this is equal. It's the same condition.
So it turns out adding a little hole doesn't do any damage. So once this is bounded, then that's no problem.
The other limit was bound. Limit of
And in fact, it's not just with the operator as from the tensor product, from the Hilbert space tensor product is continuous, which is maybe a bit surprising. Just say a word about how you then look at the modules. You can try to construct modules for these conformal nets that have this geometric picture as follows. Well, given a VOA, some state inserted, this would be a typical element of some local algebra. And so given a representation, I need to send it somewhere acting on another Hilbert space. And if you remember, what a module over a VOA tells us is a way of getting maps where now we're allowed to label the boundary components by the module. And so the obvious thing to do is now insert the same state, but label the boundary components by the module instead. So again, you can see the place that, to send the algebra, the local operator from the conformal net, is just another operator in terms of the VOA. Now this is the module operator, but at this degenerate limit. You can say the same. You now try to go and compute the index, compute the fusion rules for
So
these
the
modules.
convergence is satisfied by the same under the same conditions.
Yes, so
Of
this
these
is
modular
certainly,
operators.
if something of this form exists, it's unique, and under the conditions of the theorem. That is, if it's a submodule of the free theorem, then proof of existence. And the proof, you can see, is that the tensor product, it's not direct to see, but it's, I think, at the heart of what Antony Wassermann did. And at the heart of the proof is you show that the fusion rules for these nets directly reduce to the associativity of the geometric associativity of a VOA. There's some three modules, lambda, mu, nu. You can imagine two different ways or a couple of different ways of chalking this up, and you should have isomorphisms, the associativity isomorphisms, and those are exactly what you need to compute the fusion over here, so as Antony knew, and as works in this case as well. But I think that's about as far as I've been to that. Thank you.
Any questions, comments?
In this construction of the conformal net, you have this part which is not degenerate, which could be different, right? I mean, the inner circle could be bigger or smaller and lying here or there, and the thickness of the thing. You take them all together, or
You take them all or you take one. They generate the same net. So I can only show, so this, because this says 1 over n and not 1 over n squared, I can only show that some of them are bounded. Those are enough to generate the net, but you put in any one that's bounded, and you get the same result.
okay.
And particularly, you think if you multiply 2 of them, that corresponds to gluing along part of the boundary. And so if you multiply 2, you get a bigger one.
You also drew these pictures where you had more than one circle inside. So a conformal net is for every interval an algebra operates on a Hilbert space, but now you seem to have additional structure. You have somehow for an interval maps from h tensor h tensor h to h. Is this always so?
Well, so let's say I have something that looks like this. I could then think about drawing a bigger circle around it. And then I can erase those. That's just some vector inserted in here by the compatibility. Right? You can think about plugging this vector. So here's a map, I insert 2 points, and I get a single thing in the Hilbert space.
But you can do that in a general conformal net. It doesn't seem to be. Or is it always possible that if you have an interval, you also have maps from h tensor h to h for general conformal net? For your case, you have it somehow. So is this extra structure you get for your conformal nets? That they somehow are multilinear in some sense, not just operators?
I would expect that, I mean, the conjecture would be that you have, that any conformal net can be realized, any nice enough conformal net should be realized in this way. So I would expect to see it as a general structure. But there are lots, there's almost so many ways of constructing it that it doesn't, without the geometric picture behind it, then it doesn't, just as a multilinear map maybe doesn't mean something. But with the geometry. Yeah.
You can you can construct in your sense all of the, for example, E8 level K Bessemer-Witten models. The only question is, are they completely rational? That's what you're saying?
Yeah, so there are a lot of modules that will show up in the branching from free fermions, and the question is, are there enough? So there's 2 questions. One, does every representation of the conformal net come from a representation of the VOA? I've had two different people tell me they know how to prove that. André and also Sebastiano Carpi and Michi Weiner. So there are proofs that's something you expect that. So you know there'll be finitely many representations. You need to compute the index. So you just need to know, do enough modules show up inside the branching? So that's a question of like, let's say level 60, you know, the smallest irreducible representation of E8 inside SUN, what modules show up in the branching? And that's something I haven't looked at systematically yet. But if you know the answer to that question very well, then you can maybe prove that it's completely rational.
Any other? Can you improve the estimate putting more conditions on the curve? At least you have one good curve, right?
So I have enough good geometries, yeah. So in this case, the condition.
So this is the general estimate, but if you put other conditions.
So if this curve happens to lie in a 1-parameter group of self-maps of the disk, so that is if there's a holomorphic vector field such that you can obtain this curve by flowing along that vector field, then I know that this product is finite. So therefore, you must be able to do better than that. But it's very circuitous. It doesn't give you an estimate directly in this sense. I would love just something in this theory, just in complex analysis, to tell you to improve that, but I don't know it.
Any other question? There is no. That's time.